College Algebra, Module 10, Topic 10.3, Exponential and Logarithmic Equations, and Constructing Nonlinear Models. Objective 1, Solving Exponential Equations. Recall that the log of x base a is equal to b if and only if a to the b equals x. Again, the log is the power to which you raise the base to get x. An equation in which one or more variables occur in the exponent of an expression is called an exponential equation. The logarithmic function and the exponential function are inverses of each other. That is, they will undo each other. So, to solve an exponential equation, you can use the log function, and to solve a log equation, you can use the exponential function. Now for these examples, we're going to use the graphing calculator to solve an equation of the form f of x is equal to g of x. Then we're going to solve the equation symbolically. So if f of x is equal to 5 times the natural log of x and g of x equals 10, then we want to solve the equation 5 times the natural log of x is equal to 10. So the same thing with solving equations that we've been doing all year. We're going to let y1 be the left side of the equation, which would be 5 times the natural log of x. And we're going to let y2 be the right hand side, which will be 10. I'm going to go ahead and hit zoom 6 instead of graph so that we get our window. So there's our 5 natural log of x. There's the line y equals 10. So we're looking for this solution right there where the two lines intersect. So we are going to do second trace, which is calc. Number 5 is intersect. Enter for the first curve. Now notice when we touched enter for the first curve, it didn't do anything, so we'll need to arrow over just a little bit to make sure we're on the first curve. Enter for the second curve. And then when it asks to guess, we don't want to guess because they only intersect in one place. So our intersection is at the ordered pair x equals 7.3, y equals 10. So our solution would be x is equal to 7.389, or we could say x equals 7.39. Now if we wanted to solve this symbolically, we would do 5 times the natural log of x is equal to 10. Like we learned a couple of topics ago, first thing we're going to do is divide both sides by 5. So we get the natural log of x is equal to 2. Well, the way we undo a natural log equation is we exponentiate both sides. Because it's natural log, the base is e, so we're going to do both sides base e. Well, e to the natural log of x is just x. Then we get e squared. So we're going to do second e to the power of 2. And we get 7.389, or again, x is equal to 7.39. Now for this equation, we're going to solve and round to 2 decimal places if necessary. So option number 1 is to put it in our calculator. Left side is y1, right side is y2. The other way, pencil paper method, is we want to get the e to the negative x on the side by itself, so we're going to divide both sides by 2. So we get e to the negative x is equal to 4. Because we're looking for the power, that means log. Because the base is e, that means natural log. So we're going to do both sides. So that means we're going to take the natural log of both sides. So we'd have the natural log of e to the negative x and the natural log of 4. Well, the natural log of e to the negative x just means the power that we're raising e to get e to the negative x. So it's sort of like the natural log and the base e cancel out. So we get negative x is equal to the natural log of 4. Well, on our calculator, the natural log of 4 is 1.386 or 1.39. So if negative x is 1.39, then x is negative 1.39. Now to check it, we could just plug it back into our original problem. We would get 2 times e to the power of negative, and because x is negative, that's going to be negative 1.39. Close that, and we get 8.029, which is pretty close considering we had to round just a little bit. For the second example, again we've got an exponent, which is the variable. So first thing we want to do is get the variable term by itself. So we're going to divide both sides by 3. So we get 2 to the x power is equal to 33. Well, 2 to what power is 33? If we are looking for the power, that means we're going to find the log. The base on this is 2, so we're going to do the log base 2 of 2 to the x and the log base 2 of 33. Well, the log base 2 of 2 to the x just gives us x. The log of 33 base 2, now remember this was our change of base we did the other day, so that's the log of 33 divided by the log of 2. So on our calculator, we're going to do the log of 33 divided by the log of 2, and we get an answer of 5.04. If we want to check it, that's 3 times 2 to the power of 5.04, and we get an answer of approximately 99. Now this one's a little bit different. Even though we're looking for the variable x that's an exponent, notice these bases are the same. Well, the only way we're going to get 3 to the power of 4x to be equal to 3 to the power of x minus 6 is for 4x to be equal to x minus 6. This exponent has to equal this exponent, and notice this only works if the bases are the same. So we're going to subtract x from both sides, so we get 3x is negative 6, which means x would be negative 2. So if we wanted a different way to do this, we would go 3 to the power of, then in parentheses 4x for the left hand side, and we would do 3 to the power of x minus 6 in parentheses to the right hand side. Graph those. Notice there's our graphs, and it's real hard to tell where they intersect. We can just try it. Second trace, number 5, first curve, second curve. We don't have to guess, and we get x equals negative 2. That just shows that it does check. Okay, same thing on this equation. 6 to the power of x squared equals 6 to the power of 3x minus 2. Because the bases are 6, that means in order for that equation to be true, that the powers have to be equal, which means x squared has to equal 3x minus 2. Well, this is a quadratic because the highest power is 2. So to solve this, we're going to set it equal to 0, which means we're going to subtract 3x from both sides. We're going to add 2 to both sides. Now this one will factor. First two have to multiply to give you x squared. Last two have to multiply to give you 2. It's a positive 2, so they're either both positive or both negative. The outers and inners have to combine to give you a negative 3x. That means they both have to be negative. So when we set each of these factors equal to 0, we get x is equal to 1 and x is equal to 2. Then you need to check it. If x is 1, then we get 6 to the power of 1 squared equals 6 to the power of 3 times 1 minus 2. Well, 6 to the 1 squared is just 6 to the 1. 3 times 1 is 3. 3 minus 2 is 1. So that one holds true when x is 1. So we know that 1 is a solution. If x is 2, then we get 6 squared, or 6 to the power of 4, equals 6 to the power of 3 times 2 minus 2. So that's 6 to the 4th equals 6 to the 6 minus 2 is 4. So in this case, both of those solutions work. So our solutions are 1 and 2. Now, steps for solving logarithmic equations. If there is more than one term with a log, then we are going to write the expression as a single log on one side. We're going to do this using the properties that we learned in the last topic. Once we get it as a single log, then we're going to write that as an equivalent exponential expression. Then we're going to solve, and then we're going to check. So let's do some examples. Solve each of the following equations. The natural log of 4x is equal to 1.5. Again, we could do it on our calculator. y1 is the left-hand side, which would be the natural log of 4x. y2 is the right-hand side, which would be 1.5. When we graph those, there's our log equation. There's our 1.5. So we're going to do second trace, which is calculate where they intersect. Enter for the first curve. We've got an arrow over so that we're on the y1. Second curve is y2. We don't have to guess. And our answer is 1.12. Now if we were doing this pencil paper, we've got the log as one term. So we are going to write that as an exponential equation. Well, the natural log of 4x is equal to 1.5. That's, remember, natural log is base e, so that means e to the power of 1.5 is equal to 4x. So to get x on the side by itself, we're going to divide both sides by 4. So x is equal to e to the 1.5 divided by 4. So on our calculator, we're going to do second e to the power of 1.5 divided by 4, and notice we get exactly the same thing, so x is equal to 1.12. Second equation, the log of 2 minus x is equal to 0.5. Well, we've got a log equation. So the way we do that is we write an exponential equation that's equivalent to that, which means this is our common log, which means the base is 10. So that means 10 to the 0.5 power is equal to 2 minus x. So then we're going to subtract 2 from both sides, so we get 10 to the 0.5 minus 2 is equal to negative x. Then we're going to divide both sides by negative 1. So we get x is equal to negative 10 to the 0.5 plus 2. Or we could even rewrite that as 2 minus 10 to the 0.5 power. So we would say on our calculator, 2 minus 10 to the power of 0.5. So x is equal to negative 1.16. We could check it. The log of 2 minus negative 1.16, get an answer, and we get 0.499, which is almost 0.5. Okay, let's do some more. Solve each of the following equations. Well, we want to get the log on the side by itself, so the first thing we're going to do is divide both sides by 3, which would give us the log base 2 of 3x is equal to 1/3. Well, the way we undo a log is we do a base, So to solve a log equation, we're going to write it as an exponential, which means 2 to the power of 1/3 is equal to 3x. Because the base was 2, the answer to the log is the power. Well, to solve this, we're going to divide both sides by 3. So we get x is equal to 2 to the 1/3, or we could call it the third root of 2, divided by 3. So on our calculator, third root, remember we go to math, option number 4 is the third root of, then we enter 2, divided by 3, and we get x is equal to 0.42. Okay, and to check that, I've taken the x equals 0.42, plugged it back into the original problem. Now remember, if you have the log of 3x base 2, that's our change of base formula. So we're going to say 3 times the log of 3x divided by the log of the base, which is 2. And then we're plugging the base in as 0.42. And notice we get x equals 1.000. So we're pretty safe that that one is correct. Now second equation, this one's a little bit different because we've got 2 log terms. What we're going to do is we're going to go through and use a couple of the properties. So we're going to have the log of x squared plus 3 is equal to the log of x plus 1 squared, because remember the property says if the number's out front, that's the same as the power. So if we do this, we would get the log of x squared plus 3 minus the log of x plus 1 squared equals 0. Because we're subtracting logs, that means we can write that as a quotient. So it would be the log of x squared plus 3 over x plus 1 squared. So now what we've got is we need to write this as an exponential equation. Well, because the base is 10, that means 10 to the 0 power equals x squared plus 3 over x plus 1 squared. Well, 10 to the 0 power is 1, so that means we get 1 equals x squared plus 3 over x plus 1 squared. So if we multiply both sides by x plus 1 squared, then we would get x plus 1 squared on the right side, x squared plus 3 on the, we would get x plus 1 squared on the left hand side, x squared plus 3 on the right hand side. Now if we FOILed this left hand side out, x plus 1 squared, we would get x plus 1 times x plus 1, which would give us x squared plus 2x plus 1 equals x squared plus 3. Now to solve that, we could subtract x squared from both sides, so that would disappear, so we would get 2x plus 1 equals 3, minus 1 minus 1, 2x is equal to 2, so x is equal to 1. Now to check that, that would be the log of 1 squared plus 3, and we're trying to decide if that equals 2 times the log of 1 plus 1. Well, that's the log of 4. Does that equal to 2 times the log of 2? Well, remember the exponent rule that says you can take your the number out front and that becomes the exponent, so we would get the log of 4 is equal to the log of 4. That checks, a lot of work, but we got a solution of x is equal to 1. Now to show you this one on your calculator, we would get the log of x squared plus 3, and then the other side would be 2 times the log of x plus 1. Graph those. There's the log of x squared plus 3. The second one that came in was 2 times the log of x plus 1. We're going to find where they intersect, so we're going to do second trace number 5, enter for the first curve, enter for the second curve, We don't want to guess, and we get x is equal to 1. Now, after we've done this problem right here, I want to show you another way. Because we just have 1 log is equal to 1 log, that is the same as the log of x squared plus 3 equals the log of x plus 1 squared. Well, notice that the only way these two logs are going to be equal is if x squared plus 3 is equal to x plus 1 squared. And at that point, we can just pick up right here where we left off. X plus 1 squared equals x squared plus 3. And we really didn't have to do all this, combine all of our logs to get all the logs on one side. It just occurred to me that in order for the logs to be the same, the number that you're taking the logs of have to be the same. Okay, now this one's a little different because we've got 3 log terms. Well, remember the property that says the log of m plus the log of n is the log of mn. So on the left-hand side, we're going to get the log of x plus 1 times x minus 1 equals the log of 3. Well, if that's the case, because we've got a log on both sides, we could just go through here and say for these to be equal, x plus 1 times x minus 1 has got to be equal to 3. Well, that would give us x squared minus 1 is equal to 3. Add 1, so x squared is equal to 4. So x is equal to 2 or negative 2. Then we need to check it. If x is 2, then we would get the log of 3 plus the log of 1, and we want to know if that is equal to the log of 3. So to add logs, you multiply the number, so that would be the log of 3 times 1, which does equal the log of 3. So 2 works. What about negative 2? Well, if we plug negative 2 in, then we get the log of negative 2 plus 1 is negative 1. The log of negative 2 minus 1 is negative 3. But remember, you cannot take the log of negative numbers. Therefore, the negative 2 is not going to work. Now, what would this look like on our calculator? There's the log of x plus 1 plus the log of x minus 1. There's the log of 3. Notice they only intersect in one place. Second trace, which is calculate number 5. First curve, we'll need to arrow over to make sure we're on the first curve. Notice we're not on the first curve for a while until we jump all the way over to 1. Then second curve, and then our guess, and we get an answer of x is equal to 2. Now remember, this negative 2 is what we call an extraneous solution. It appears to be a solution, but it's really not. It's sort of an extra solution. So when you're writing the solution for this equation, all you're going to write down is x is equal to 2. Objective 2, solving equations graphically. Sometimes it is not possible to solve these equations symbolically, so we must use the graphing calculator. So use the calculator to solve this equation graphically. Round to the nearest hundredth. So the first equation is going to be the left-hand side, which would be x squared minus x times the natural log of x. Then the right-hand side would just be 2. So there's our x minus x natural log of x. There's our 2. Second trace, which is intersect number 5. Enter, again, we've got to move it off of 0. Second curve, we don't want to guess. and we get a solution of x equals 1.71. Objective 3, applications. In terms of applications, exponential functions and equations are used to model rapid growth. Remember, your exponential function looks like this. Logarithms are used to model slower growths. Remember, logarithmic graphs look like this. A logistic function will be introduced later in this section to model situations in which the data increase slowly up to a point, then they increase pretty fast, and then they start to level off. So we've got exponentials that go big really fast, we've got logs that level out, and then we're going to have these logistic functions later that sort of increase and decrease both. So an example, the number n of E. coli bacteria in millions per milliliter after t minutes can be modeled by the function n of t is equal to 0.5 e to the power of 0.014 t. Determine the elapsed time required for the concentration of bacteria to reach 25 million per milliliter. So the 25 million per milliliter is the number of minutes. So that's the y value. So what we're going to have is 25 is equal to 0.5 e to the 0.014 t. And we're trying to solve for t. So the first thing we're going to do is divide both sides by 0.5. So we get 25 divided by 0.5. And that would give us 50. So we get 50 is equal to e to the 0.014 t. Well, we're trying to find the power. So to find the power, we do the log. This is base e, so we're going to do the natural log of both sides. So the natural log of 50 is equal to 0.014 t. So to get t by itself, we're going to divide both sides by 0.014. So t is equal to the natural log of 50 divided by 0.014. And that would give us a time of 279.4 minutes. Another example. The number of Atlantic bluefin tuna in thousands X years after 1974 can be modeled by the function f of x equals 230 times 0.881 to the power of x. Estimate the year, or the x value, when the number of bluefin tuna reached 95,000. Well, because x is in thousands, we're going to say 95 is equal to 230 times 0.881x. Again, we're looking for x, so we're looking for the power. So the first thing we're going to do is divide both sides by 230. So we get 0.413 equals 0.881 to the power of x. Well, if we're looking for the power, that means we're going to do the log base 881 of both sides. So that means x is equal to, now our change of base formula says the log of 0.413 divided by the log of 0.881. And when we do that, we get x is equal to 6.918 or 6.92, let's say 7 years. So it's 7 years after 1974, which means our year would be 1981. 230 times 0.881 to the power of 7, and we would get about 95,000. Okay, now this is a little bit different application, and we're going to use this to show a different way to use our calculator. The height of a tree in feet after X years is listed in the table. So let's enter the values into our calculator. So remember, we go to Stat, we go to Edit, we're going to enter our values. So we have 1, 5, 10, 20, 30, and 40 for our X values. Then we're going to arrow over our Y values would be 1.3, 3, 8, 32, 47, and then our last value would be 50. Now our directions say, make a table for f starting at x is 10 and incrementing by 10. Well, what you've got to know is that the height of a tree is modeled by a logistic function, which means the tree starts out growing very, very, very slowly. Then it takes off at the middle and it grows pretty quick, and then as it gets older it levels off just a little bit. So the way we would do our logistic function on our calculator is we would come in just like we did the regression. We're going to go to Stat, we're going to go to Calculate, and we're going to go all the way down to AB, which is logistic. When we select our logistic regression, it takes forever because it's a pretty ugly formula. And notice our formula is y equals c over 1 plus a e to the power of negative bx. Or then they give you the numbers for a, b, and c. So what our formula would look like is f of x is equal to c, which is 50.19, divided by 1 plus a, which is 47.44, e to the power of negative 0.22x. Okay? Now, one thing that I may not have shown you yet is if we wanted to graph that line or that curve, we would go to y equals, and then we would have to type that in. And because there are fractions and powers and all that, the parentheses can get a little tricky. So there's a way to get that formula onto your calculator without having to type it in. So what you're going to do is you are going to start out with vars, which is right beside the clear button. First thing you're going to do is go down to number 5, which is Stat, because that's where we put everything in our problem. Then we're going to arrow over 2 places to where we get to equation, because we are looking for the logistic equation. Then option number 1 is regression equation, because that's the one that we're looking for. Well, when we do that, notice it puts that whole formula into your y equals. So now when we graph that, our picture looks like this right here. Notice it's going up very, very slowly, and then it's going to take off. But what I wanted to show you was over here in the table. So if we go to second table, as the x values get larger, the y values get larger. And if we go all the way down, we're trying to find if there's a maximum height of that tree. We notice we just keep going, going, going. So what the direction said was, let's make a table, let's start it at 10, and let's increment it by 10. So what I want to do is I want to go up here, it's hard to see, but right above window it says table set. So what I want you to do is I want you to go into second table set. We are going to start our table at 10. Now that triangle table means change in table, so we want to increment it by 10. Now when we go to second table, notice when x is 10, or when the tree is 10 years old, the height is 8 feet. After 20 years, it's 31 feet tall. After 30 years, it's 47 feet tall. And notice, but you notice as that tree gets older and older, what happens? That tree is never going to go above 50.187 feet. Okay, after 300 years, it's still sitting at 50.187. So our question says, graph F and identify the horizontal asymptote. Okay, well the asymptote is just that horizontal line. So for ours, it never crosses that 50.187. So it's going to go up and it's going to get closer and closer and closer. So our horizontal asymptote basically is just going to be the line y equals 50. Then our next question says, determine after how long the tree was 25 feet. So if we go back in our table starting at 0 incrementing by 10, and we're trying to find when the tree was 25 feet tall, notice that it hit 25 feet tall between 10 years and 20 years. Okay, so I'm just going to make a note here. It's between 10 years and 20 years. So now what we can do is we can go back and go second table set. Let's start it at 10 and let's increment it by 1. So now when we do second table, notice we're going from 10 but we're increasing by 1 every year. So we know that it hits 25 years between 17 and 18 years. Okay, now if we wanted to get a little bit closer, we could say, okay, let's do it again. Let's go to second table set. This time, let's start our table at 17, and let's increment it by 0.1 years. So now when we go second table, that gives us the value, and notice we hit 25 years between 17.4 and 17.5 years. So I would say that after 17 years, the tree hit 25 feet. Okay, which makes sense because 25 feet would be somewhere down here between the 10 and the 20. We're going to do some more logistics later, but I just wanted to show you how you could use the table to do this instead of just doing it on your calculator. Okay, objective 4 is modeling. Do you remember the 3 possible models we just talked about? If the graph is getting large very quickly, that was our exponential model, which is y equals ab to the x. The second graph, they get larger, but they get large very slowly. That was our logarithmic graph, and our formula looks like y equals a plus b times the natural log of x. And then our third function, notice on this one it starts out real slow, then it gets large quickly, and then it levels out and it gets large very slowly. This is the one I was telling you about, which is your logistic function, which is c over 1 plus ae to the negative bx. So the first thing we're going to do is try and determine which model best represents a set of data. And it is extremely useful to look at a scatter plot of the data. So remember, to get a scatter plot on your calculator, you're going to enter your data in the stat, put your x's in L1, your y's in L2. Then you're going to go to stat plot, which is second y equals. Third thing you're going to do is adjust your window size, so you're going to go to zoom 9, and then you're going to graph it, and then you're going to pick which of the 3 best fits your data. Okay, so let's do a couple of examples. The table below lists the interest rates for certificates of deposit during January 1997. Use the data to complete the following. So the first thing we're going to do is go to Stat. We're going to choose Edit. We need to clear what was in there, so we're going to go to L2, hit Clear. Go over up to L1, hit Clear, press Enter. Because they give us times in months and years, I'm going to just do everything in years, but the first one, 6 months, I'm going to call that 0.5 of a year. the second one would be 1 year, the third one would be 2.5 years, and the fourth one would be 5 years. Then on the second one we've got 4.75. The second one is 5.03. The third one is 5.25. And the fourth one is 5.54. Well, when we do that, we're going to go to Second Stat Plot, enter to turn it on, enter to select the dots. We're going to go to Zoom 9, which is Zoom Stat. So our first question says, what type of function might model these data? So that looks more like a logarithmic model than the other two. The second question says, use the least squares regression to find a function that models the data. So we're going to go to Stat, Calculate, and we are going to go down to find the logarithmic. Now the logarithmic is the natural log regression, is what that looks like. So we are going to choose number 9, press enter. So our logarithmic regression looks like a plus b times the natural log of x. So our function is going to be y equals 4.99 plus 0.33 times the natural log of x. And then C part says use the function to estimate the rate for a 4-year certificate of deposit. Well, the year is the x value, so we're going to take our function 4.99 plus 0.33 times the natural log of 4 because it's 4 years. And we would get an answer of 5. Okay, another example. One of the earliest studies about population growth was done using yeast plants in the year 1913. A small amount of yeast was placed in a container with a fixed amount of nourishment. The units of yeast were recorded every 2 hours. So here's the data, given time every 2 hours and the units of yeast that were present. So if we enter this in our calculator, so we are going to have 0, 2, 4, 6, 8, 10, 12, 14, 16, and 18. In the y values, 9.6, 655.9, 661.8. So the first thing we want to do is look at our picture and try to determine which of the 3 types of graphs we're going to get. So when we do that, we're going to go second, y equals, enter to turn it on, enter to select it, and again we're going to go Zoom 9, which is Zoom Stat. Now notice this one, it increases and then it levels off. So this one is going to be a logistic function. B part says use the regression to find a function that models the data. So what we're going to do again is we're going to go to Stat, we're going to go to Calculate. Now remember, logistic is all the way down to AB. Press enter and we get our ugly formula. Remember, this one takes a long time. Okay, so this one is C, which is 661.8 divided by 1 plus 74.5 e to the power of negative 0.55x. And then C part says approximate the time when the amount of yeast was 200 units. Round to the nearest tenth of an hour. Well, now if they gave us the x value, or if they gave us the number of years, then we would plug it in for x. Because they're giving us the amount of yeast, that means we're going to plug it in for y, so we would get 200 is equal to 661.8 over 1 plus 74.5 e to the negative 0.55x. And again, to solve that on our calculator, we're going to go to y equals, I'm just going to go to VARS. Number 5 is statistics. slide to equation number 1 is regression equation, and I know there's a lot of data points that we don't need. We could either leave them in there, or I could do 661.8 and delete all those extra numbers over 1 plus 74.5 and then delete the rest of those numbers. And I really don't think it would matter one way or another if we just left them in there. And then y2 is going to be 200 because that's what we're trying to set it equal to. So I'm going to go to zoom 0, which is a zoom fit. So there's our function going through there. There's the 200 line. So we want to find where those are going to intersect. So we're going to go second trace, number 5, enter, enter, enter. So when the y value is 200, the x value is 6.3. So that means in 6.3 hours, the yeast units is going to be 200. Okay, last example. The National Institute for Automotive Service Excellence reported that the number of females working in automotive repair is increasing. Here's the data that represents the year that they did the survey and the total number of females working in automotive repair. We're going to go to Stat. We're going to go number 1 to Edit. So we're going to have 0, 1 through 7. And then the Y values, we're going to have 556, 614, 1592. So again, first thing we have to do is decide which graph this looks like. So we're going to go second stat plot, enter, enter, zoom 9, which is stat. Notice this one is exponential because it increases very quickly. So we are going to go to Stat, Calc. Now exponential, we're going to arrow down to 0, which is exponential. So our first question said, what type of function is f of x? So we're going to say exponential. Then it says use the least squares regression to find the function. Well, that's what we just found. So when we press enter for exponential, our standard formula is y equals ab to the x. So when we plug our numbers in, we're going to get y equals 507.11 times b, which is 1.17 to the power of x. And then the last question says, use the function to estimate the number of certified female technicians in the year 2005. Well, the 2005 is the year. Now, it's the year since 1988. So 2005 is how many years since 1988? That would be 17. So we're going to go into our problem, or into our function. Everywhere we had an x, we're going to plug in 17. So we are going to do 507.11 times 1.17 to the power of 17. And that means in the year 2005, then we would expect there to be 7,316 female workers. Okay, so remember, if they give us the years, we're plugging in for x. If they would have given us the total number of female workers and asked what year that would be, then we would set it equal to the function. Okay, you are now ready to do the homework for topic 10.3 in my math lab. Once you have scored at least a 90% on each of these 3 sections, you will be ready to take the Module 10 quiz. Then, once you have scored at least an 80% on the Module 10 quiz, you will be ready to take the final exam. remember, you must score at least a 75% on the final exam in order to pass the course.